need to know for this exam that you've got to revise? Well, first, rates of reaction. So that's what we did in the 2061. And there you looked at the important things that affected rate of reaction. So first of all, your substances, your particles have to collide, and they have to collide with enough energy to overcome that activation energy. And then the other one was also they have to be the right orientation. They've got to collide in the right way. If they collide where the wrong atoms are together, then nothing's going to happen. And then you had the factors. You had to explain the factors. So what happens when I change my concentration? What happens when I change my temperature, my surface area, and add a catalyst? So you need to be able to explain all of those specific to any given reaction. So in other words, don't talk about surface area when you get given a gas, or don't talk about concentration when the reactant is a solid. So just make, don't just parrot learn it. Look at what you've got and the states they're in, and then build up your argument. Then what we looked at was the equilibrium, how it works, and the equilibrium constant. So what is equilibrium and what affects it? So remember the dynamic nature. Is this all clear to see, or is this a little bit too small? Must I make it bigger? It's readable. Okay, great. So the dynamic nature is just basically, if something's at equilibrium on the macro level, your observations, it doesn't look as though anything is happening, but on the micro level, things are happening all the time, and the rate of the forward reaction is equal to the rate of the back reaction for a reverse reaction if something is in equilibrium. And then we looked at also factors, and some of these are very similar to the what affected rates. So just make sure you don't get yourself confused. So temperature, concentration, pressure will affect an equilibrium. A catalyst will not. So it says here the effect of changes in or addition of a catalyst. So that's the one that's not going to affect your equilibrium. And also remember that temperature also changes the value of the equilibrium constant. So that is also something to remember. So the equilibrium constant is a constant until you change the temperature, and then it changes. And we'll look actually at that just now with water, because we're doing acids and bases. And so we look at basic for homogeneous solutions, which means everything must be in the same phase. So it'll be like a mixture of gases or a solution. So you'll be looking at things like that. And this is what we are going to be doing in this lesson. So it's what is an acid, what is a base? What is a strong acid, what is a strong base? And what is a weak acid, what is a weak base? And how do we know what we've got? If we look at some properties like conductivity, how well it conducts an electric current, how quickly something will react in a strong acid or a weak acid, and then the pH. So those are the three things we have to look at. And then we do calculations. Now we've already done some calculations with an equilibrium constant, but we'll also be doing pH calculations. So that's the standard. And do you think it's all pretty doable? Yeah, great. Okay, so let's look at acids and bases. Now, I've got water over here. So water molecules, if I show all my water molecules, so I'm showing my solvent, you can see I've got hundreds of thousands, millions, Googleplex, not quite, of water molecules. In fact, water is around about 55 moles of water molecules in a liter. So there are lots and lots and lots of water molecules. But water isn't only H2O. Sometimes it breaks up to collide and one water molecule will grab the hydrogen off the other one. So you get the hydronium ion or the H plus ion. Remember H plus? H stands for what element? So Hayden is typing. And now you've stopped typing. Does anybody want to say what element H is? Okay, quite a few of you typing. Great. Hydrogen. Good. How many protons does hydrogen have? 1. And how many electrons does hydrogen have? Correct. How many neutrons does the normal hydrogen isotope have? 0. So if you think of what hydrogen is, it's simply a proton with one electron moving around it. So if I remove that electron, all we've got is a proton, which is a very, very, very small particle. And because it's got a full positive charge on it, it's going to be have quite a big charge value relative to its size. So in other words, what I'm trying to say is a proton is going to be really strongly attracted to anything that's got an electron-rich area. And oxygen, if you remember from your 2.4 standard, those Lewis structures has got 2 lone pairs of electrons, and that's why, because these are fairly naked in that there's a strong pull of the oxygen pulls those shared electrons much more closely to it, leaving the hydrogen pretty, as we say, pretty naked. It doesn't really have much electron density around it at all. And so it's quite easy when 2 water molecules collide to actually drag off one of those protons. And then we form the hydronium ion and the hydroxide ion. And then they may collide, and then that would form water again, and there'd be other collisions. Or one of these hydronium ions might collide with another water molecule and transfer its extra proton onto. So it's in constant equilibrium between any of the water molecules and any hydronium ions or hydroxide ions formed. Okay, so that's when we have pure water, and if I dip in my pH meter, it's going to have a pH of 7 at 25 degrees, actually. Why I say that is I'm going to show you, I think it's this one. Here is an example of what happens when you change things. So if I make this 25 degrees, notice that I should actually clear it and then first make it 25 degrees. If I calculate my pH of water, it's going to be pretty much 7. Okay, you can see it neutral of 7. If I change my temperature, if I increase my temperature, and I calculate now, so it's now, I'll make it close to boiling. Okay, notice what's happened to the pH. It's dropped to nearly 6. So boiling water does not actually have a pH of 7 if it's totally neutral. We still have a equal number of hydroxide ions to hydronium ions, so it's still neutral, but what happens is my equilibrium constant has changed. So in other words, if I go back here, we've now got more hydronium ions. So as we heat up this water, then the equilibrium is going to shift towards the right. So does that tell you whether this reaction is exothermic or endothermic? It's good revision from last week. If I increase the heat and the equilibrium shifts to the right, so that means if it goes to the right, it's losing heat. or giving off heat. So the forward reaction, yep. So, Thomas, you're correct, because if I'm adding heat, it's got to remove that heat. And it removes that heat by absorbing it and making it endothermic. So yes, so this is endothermic going to form the hydronium hydroxide ions, and if they collide, it forms water, and that's the exothermic. It's not particularly what you need, but it's a good way of working out, do you know how equilibrium constants work? And so, of course, if I cool it down, so if you're in the Arctic waters, you know, around Antarctica or the Arctic, and I calculate, can you see it's a lot more basic? So again, we've got equal numbers of hydroxide and hydronium ions now, but we've got fewer of them. And because we've got fewer of them, the pH has increased. So we will be doing that calculation, and then you can see how it works. But let's first go on back to here. We've got water, and we've looked at that equilibrium. Now we're going to look at a strong acid. Now if it put in a strong acid like HA, it could be hydrochloric acid, nitric acid. A strong acid, by definition, dissociates completely. So if it dissociates completely, will I have any HA molecules in solution? So if I put in HA and it dissociates completely, will I have any HA? Who would like to be brave enough to have a guess? Correct. There won't be any, because the HA has completely split up into the H plus and the A minus. So that's what we've got here. The HA has reacted with the water, and it's completely split up to form the hydronium ion and the A minus ion. So notice that the pH has dropped to 2. If I used an indicator and dropped it down, you can see it's gone, you know, red. And it's because I've got a lot of hydronium ions. Okay, I can show it by a graph, and you can see I've still got tons of water molecules because that's my solvent, but I have got no HA. It's pretty much not measurable, and I have got equal amounts of A minus and hydronium ions, and I've got 1 times 10 to the minus 2, and when we do the calculation you'll see how we get a pH of 2 of that. So that's a strong acid. So you just have to remember, strong acid by definition dissociates completely. Now you have to know some of these strong acids off by heart. So in the exam, if they give you something, they expect you to recognize that it's a strong acid. So those are HCl, nitric acid, sulfuric acid, with respect to the first hydrogen. It's not really for the second one, but to all intents and purposes it's close for both. And then there are is HBr and HI. There are a few more, but the 3 most important ones would be hydrochloric acid, nitric acid, and then the sulfuric acid. So make sure you recognize those as strong acids. Okay. The other acids are weak, and again you are expected to recognize a few of those weak acids. Ethanoic acid is a weak acid. Where do you come across ethanoic acid in your home? Most people have a bottle of it sitting in their pantry somewhere, or in their cleaning cupboard. Vinegar. Okay, it's a weak acid. Now, weak acid doesn't mean to say it's not poisonous or anything like that. What weak means is that it will not completely dissociate. So if we look at this equilibrium, can you see I've got my arrow going all the way to A minus and H3O plus, because my reaction goes all the way to the right. It dissociates completely. If I click on a weak acid, can you see we've got that equilibrium arrow? So that's because only some of the HA will dissociate. So you can see I've still got most of it sitting as HA, and only some of it has broken up to form the A minus and the hydronium ions. So can you see we've now got less hydronium ions compared to the strong acid where we had more hydronium ions. And the pH is a function of the amount of hydronium ions. So that's why it's now got a lower it's a higher pH because it's an inverse function, sorry. So I've got fewer hydronium ions, so you can see my, if I match the color, it's round about a pH of 6 roundabout, and that's because I've got fewer hydronium ions. I can show that like this, so you can see I've got lots of HA molecules and not as many hydronium ions or the anions. So if I flick between there, I've got lots of hydronium ions, there I've got fewer. Okay, now remember what we said with the standard, you had to explain it, the effects on reaction, conductivity and pH. So let's have a look at conductivity. If I put a system together to try and measure the current that goes through, so I have a battery. If I have a weak acid and I dip in my electrodes, can you see that my light bulb is lighting up? So does a weak acid conduct electricity? Yes. Okay, it does. Why does it conduct electricity? Think of what electricity is. Electricity is a movement of charge. So what you've got to ask yourself is, do I have any charges in solution? Abigail, fantastic. Okay, I have got ions in solution. Ions are charged particles. So both the A minus and the hydronium ions, they both charge. So when they move, the negatives will move to the positive pole and the positive will move to the negative pole, but they'll be moving, and so they will be conducting a current. Okay, if I have a strong acid, what's happened to the light bulb? Is it, so I see, yeah, it's brighter. So do you think that sorry, I've gone blank. Do you think I've got more electricity being conducted there, a greater current or a smaller current? Greater. Correct, well done. So why would that happen? If you have a look, remember we said electricity is a flow of charge, and those are my charges, my ions. Right, well done both of you. There are more ions in solution. So the way you would explain it is, you may be given a whole lot of acids and said this one's got high conductivity and this one's got low conductivity and so on and so forth, and you may then be asked which one would be a strong acid and which one would be a weak acid, so you could work it that way. Or you could be given, say, HCl and ethanoic acid, and you could be asked what would the conductivity be like, and so on. And so you would point out that a strong acid would dissociate completely to have lots of ions in solution, so it can carry a greater current than a weak acid, which only partially dissociates, so you've only got a few ions in solution. Okay, now let's look at a strong base. So I'm just going to move this out first of all. A base is, if you like, the opposite of an acid. It's something that doesn't release hydronium ions in solution, or protons, because remember, we say an acid is a proton donor because an H plus ion is only a proton. A base is something that releases hydroxide ions in solution. Okay, it's a proton acceptor, because as we saw from that water equation, we know that hydroxide will react with the hydronium ions or a proton to form water. Is that clear? So can you see why the hydroxide is called also like a proton acceptor? Okay, so there's no response, so I'm not too sure. So let's go back to strong base. So if we've got any hydroxide, it'll accept a proton very easily. So any metal hydroxide like sodium hydroxide, lithium hydroxide, even calcium hydroxide and magnesium hydroxide, even though those aren't particularly soluble, anything that does dissolve in water will be completely dissociated into the metal cations and the hydroxide anion. And can you see I've got lots of ions in solution and I've got no sodium hydroxide as a molecule sitting there anyway. It's broken up completely. So do you think my light bulb is going to glow very brightly or not that brightly or not at all? Very brightly. Okay, and there it is. So it's like the same as a strong acid. It'll glow very brightly because I've got lots of ions in solution. And then I think you can see with a weak base doesn't dissociate very much. So an example of a weak base would be your ethanoate anion. Ammonia is a weak base. There are a lot of weak bases. If you've done organic chemistry, we had some lessons on that earlier, and remember we had, for instance, methylamine, or methanamine, sorry. Methanamine or ethanamine, those are all weak bases. Anything with a nitrogen in it will be basic. So the base reacts with a proton, with water, accepts a proton. So this is like your ammonium ion, NH4+. It's accepted a proton, so it's become positive. And of course water has lost a proton, so it's negative. And if I now change my pH, if I change that to a pH meter, can you see I have got an even bigger increase in my pH? So what can you tell me about the hydronium ions? Have I got more hydronium ions or fewer hydronium ions than when we looked at the strong and weak acid? So in other words, if I go to a graph, it'll be fewer. Because remember, the fewer hydronium ions we have, the higher the pH. There's an inverse relationship. And you can see over here, we don't even have the hydronium ions showing. There will always be a tiny, tiny bit here, and when you go into level 3, you'll deal with it. So we don't have very many hydronium ions at all, and it's basically all the hydroxide. Okay, so you're welcome to just Google PhET, and if you Google PhET acid and base solutions, it will, it'll work off any platform because it's HTML. So if you've got an iPad or a Windows 10 or something like that, it should work. You can also play around by changing your concentration, because remember that other part is what happens when you change your concentration in terms of reactivity, but also in terms of pH. Now we haven't done the equation yet, but if I say, for instance, increase my, actually let me first do it there and make it a strong acid. If I increase my concentration, can you see my pH is going down and down and down because I've got more hydronium ions. So the question is, if I have a strong acid, can I have a pH of 6 for a strong acid? Yes. If the solution is dilute enough, I would have decreased my hydronium ion concentration, and so it'll go down. So if I decrease my concentration, okay, I'm only going to 0.001, so it's only going to get to 3. But if I decreased it even more, then it would go down even more. So you could have a strong acid solution, so a solution of HCl, as long as it's dilute enough, it can have a pH of 6. Okay. Could it have a pH of 8? Not too sure. It's unlikely because you would have had to have, it couldn't just be a pure solution of HCl and water. You would have had to have added something else. Unless, of course, you change the temperature as I showed you before. But I'm talking about standard temperature. Okay, so as long as you're clear in your mind that the pH depends on the hydronium ion concentration. So if I'm comparing a weak acid and a strong acid of the same concentration, then which one has the lower pH, the strong acid or the weak acid? So I see Abigail's typing. The rest of you can... Okay, Thomas is typing, great. So remember the question was, if I have a weak and strong acid of the same concentration, which one would have the lower pH? The strong. Okay, because all else being equal, the strong acid is going to release more hydronium ions in solution. But if I have them of different concentrations, then I can't automatically say which one will have the lower pH. I'd have to calculate it. Okay. At level 2, you don't do calculations of weak acids, you only do calculations of strong acids. You'll do calculation of pHs of weak acids next year. Okay, so that's quite a nice simulation to play around with and just getting your idea what's happening at the particle level. Because if you've got a picture of what's happening at the particle level, I think chemistry is pretty easy. So these simulations are great for that. Now, the pH scale is another simulation by FET, and what this is useful for is it shows you what happens to the hydronium ions and the hydroxide ions. So I'm just doing logarithmic, okay? So if I just change my solutions, so drain cleaner, for instance, is pretty basic. Can you see how OH has gone down and the hydronium ions, well, has gone up? Sorry, it's become more concentrated. Hydronium has gone down by pretty much an equal amount. If I do blood, then can you see that one's dropped by an equal amount? So what can you tell me about the concentrations of those two? If I multiplied them together, would it always come to the same value? Yes, and that value would always be 10 to the minus 14. And what's special about that particular value, 10 to the minus 14? So if I go back here, 10 to the minus 14 is the equilibrium constant for this equation. So going back to what I was showing over here, if I have it at, of course, at 25 degrees, then, okay, that is 101. It should be, haven't perhaps got it quite exactly on there. But basically at 25 degrees, then my equilibrium between my hydronium and hydroxide particles to all my water molecules is 1 times 10 to the minus 14. Okay, this value is very small. So what does it tell you about the number of hydronium ions compared to the number of water molecules? Because remember, my equilibrium constant is products over reactants. So products, the concentration of products multiplied together divided by the concentration of the reactants multiplied together. So what does that tell you if Kw is so small about the concentration of these ions? They're very small, very few, so it's a much smaller proportion of the products. Well done, Abigail. Okay, so you've got that idea. And so what this does, it allows you to work out the pH from the different, you just put in a number in any one of these. So if I have a pH of, let's say, 2, and I calculate, should fill in the other blocks. Okay, notice what these add up to. 2 and 12 add up to 14. Okay, if I have this as being 5 and I calculate, 5 and 9 add up to 14. And you can put in any thing, you can put 3.52 and you calculate. Okay, it's obvious that doesn't take 2 decimal places, but notice it'll still add up to 14. And this is all calculations done, of course, at 25 degrees, when kW is equal to 10 to the minus 14, because can you see if you multiply those two figures together, okay, if you multiply them, so can you all see my calculator here? So if you've got a calculator on hand, then you can do it yourself. But pretty much if I said 3 exponential 4 minus, and I multiplied it by 3.3 exponential 11 minus, and if I rounded it off, okay, 9.9 times 10 to the minus 15, which I hope you realize is close enough to 1 times 10 to the minus 14. Okay, if you rounded it off. So whatever my values work out, my hydronium and hydroxide ion concentrations, if I multiply them together, will always give me 10 to the minus 14. And my pH, if I add my pH with the pOH, I'll always get 14. Okay, so what I want to do now is look at some calculations. So, the equation you need to know to calculate the pH is this one. Okay, so you need to learn that one off by heart. The next thing you also need to do is work out how to do logs on your calculator. So do you all know how to use logs on your calculator? Okay, so the dissociation of water, Abigail, should be endothermic. Because when you heat it, you get more hydronium ions. So it's going to favor the endothermic reaction. Because the stress is adding heat, so the way the reaction works is to remove the heat. So if it goes forward, that means that must be an endothermic because it's absorbing heat. Okay, so if you're not sure on how to use your calculator, I know some of you have said yes, but not all of you, work with just straightforward numbers that you know. The way a log scale works is that a log of 1 has a pH of 0. So this is the log value. Okay, if I have, sorry, no, it's the other way around. So this is the log value, this is the number. So your normal numbers. Okay, so 1 will have a log of 0. 10 has a log of 1. 100 has a log value of 2. 1000, can you get the picture, is a log value of 3. Basically what your log scale is doing, it's giving you how many decimal places there are. Well, not so much decimal places, but how many values you've got. Now, your math teachers must probably got a much better name for this. So you can see, you know, I've got 2 placeholders there, I've got 3 placeholders there, and you would carry on. So, you know, 4 would be a log of this number. Okay, so that's the relationship. So you can see if you go up 1 unit in the log scale, you going up by quite a large percentage in the normal number scale. Okay, so if you type into your calculator 10,000 log, if you don't come up with the answer of 4, then your calculator may be different. Perhaps you have to say log first and then 10,000 or something like that. So make sure you know how to use your calculator. Also, we can go the reverse. I can have, if I have -1, then I've got so 10. So 1 times 10 to the -1. In other words, that is going to be 0.1. And then 0.01 is going to be 1 times 10 to the -2. So this number, can you see, will be, if I take a log, I'm going to get -2. Do I need to explain anything more on this? Because then if I carry on 0.001, it'll be 1 times 10 to the -3, and then I'll have a log value of -3. So again, if you can see it as being a placeholder, you know, then it would make more sense in your head. Okay, the negative tells you we're now going in that direction, whereas the positive tells us we're going in that direction. Okay, so knowing that about logs, then what I want to do is now work out some calculations. For a strong acid, remember we said a strong acid dissociates completely. So if I have 0.100 mole per liter of HCl, I put that into solution. How much H plus have I got? Or hydronium ion? What would it be? So Abigail is typing. Stop typing. And we can also say how much chloride ion have I got. So if I had 0.1, remember the HCl breaks up completely into plus ions and chloride ions. So how much have I got of each ion? Nobody want to have a go? Okay, can you see, remember my equation was going all the way to H plus Cl minus. So I'm going to land up with nothing over here, okay? And I'm going to have then 0. Oh, you've really gone ahead. I'm going to have 0.1 over here, and I'm going to have 0.1 over there. Does that make sense? If I started off with 0.1 and then it all splits up, I'm going to have 0.1 of each. So this is the number of, this is the concentration. So do you all see that I'm going to have 0.1 mole per liter for each ion? Okay, right. Now that I've worked out my concentration of hydronium ions, because remember that is what is in the formula you have to learn. Now I just substitute. So I say pH is equal to the negative log of, now the square brackets means hydronium ions, means concentration. So make sure that you put in the square brackets. And then you substitute your value, which is 0.1, so it's equal to minus log. Notice that I'm showing full working. You should always show full working. And if I now go and get my calculator up, okay, now I work out my value, so 0.1 log. So I've got, can you see it's minus 1, that's just the log. So I've got minus 1, because can you see that I've done just simply that thing. So I'm going to get overall a pH of 1. Okay, you don't have to perhaps put in that step, but because you just do that in your calculator. Now, just a few tips. You should do your pH, because remember, for excellence, they are always looking at significant figures. And the other thing they're always looking at is units. Okay? So, pH doesn't have any units. Concentration has units, but pH does not have units. So you wouldn't put any units over here. Okay? But significant figures. Now, log scales work slightly different with significant figures than, you know, what you calculated for the rest. Because remember what I said, this 2 is just simply showing the placeholders, like I've got 2 over there, I've got 3 over there, so it's just telling me how many noughts I've got or how many in front of the decimal place. So I strongly recommend that when you put in pH, to make sure you satisfy any examiner, because examiners vary with their opinions, so to satisfy any examiner you would put in 1 or 2 decimal places, not more than 2. Now, I know I explained when I was doing significant figures, and I think it was 2011, if you did that booklet, there is something, and I've explained how log significance figures work, but just in practice, to make sure you get the right grade, is just use either 1 or 2 decimal places. Okay, so if I go and I do now a pH, so say I had now a 0.532 mole per liter of nitric acid. As I say, you'll only be given strong acids or strong bases. So the first thing you do is you work out, well, what is my concentration of hydronium ions going to be? And because it's a strong acid, this will dissociate completely. So I'm going to have 0.532 moles per liter of hydronium ions. Okay, so it's fairly straightforward. Whatever acid you've been given, you've got the same concentration of hydronium ions. So now you just simply say pH is equal to negative log of the hydronium ions. And so what you would do is it's minus log of 0.532. And if I do that calculation, so it's the same sort of thing. You go 0.532 and you do a log, and can you see you've got, if it's clear enough, negative 0.274. Wait, was it 274 or 0. Yeah, 0.274. So 0.2, I'm just wondering if I made a mistake there. Let me just try again. So 0.532 log. Okay, no, 274. Okay, and then that would be negative times the negative. It'll be 0.274 pH, and as I said, rounded off to two significant figures, two decimal places. So that would be what? 0.27 or 0.28? What would it be? 0.27, correct. Okay, and again, there's no units, so that would be your answer. Okay, so do you think they're pretty straightforward? So you can see the more hydronium ion concentration, the lower the pH. Okay, if I now do the other way, say I've got a base, so let's just use blue for base. So say I had a 0.1 mole per liter, let's give it some significant figures, mole per liter of sodium hydroxide. Okay? So do I have any hydronium ions present there? Because remember, my sodium hydroxide will react with my water to form Na plus and OH minus. So do I know the hydronium ion concentration? Okay, Thomas, you say yes. What would it be? Because indirectly you're correct. You could work it out. I was just doing it on the surface level. Okay, that's not the hydronium ion. That because can you see I've got no hydronium ion in my equation. So if I do the pH is equal to negative log of H3O plus, I don't have H3O plus there. The only thing I do have is the OH, and we know that OH and H3O plus are related. So if I work out the POH, I can work out the pH. So in other words, what you're going to do here now is not work out the pH, you're going to work out the POH. So the POH would be the negative log of, what do you think? What concentration of iron would I put in there? Anybody want to have a guess? Okay, correct, Nicholas, you put the value in. I just wanted you to get the POH is looking at the negative log of the concentration of the hydroxide ions. Okay, and you quite correctly said that it's going to be 0.100. Okay, and we know from previous times it's going to be a POH of 1 if you did the calculation. Now, you were asked for the pH, not the POH. So how can I find out the pH from my POH? And this is the other equation you should really know, is that the pH plus the POH is equal to 14. Correct, Abigail, you got it there. So the pH is equal to 14, subtract the POH, which is equal to 14 subtract 1, and so the pH is 13. Okay, so should we do one more example where we have you know, more of an odd figure? So say we had, say, naught, or let's, yeah, 0.267 moles per liter of potassium hydroxide. Okay, that's a strong base. So the first thing you do is you work out, have I got the hydronium ions there or the hydroxide ions? In other words, am I going to be using pH or am I going to be using POH? So see, Hayden is typing. And if you're not sure, you always write equations to help you, because the equations will help you. They're nice representations of what is happening at particle level. I mean, it's got its limitations, but okay, so I think, is that what you were going to say? I was hoping you were going to type the answer there. Yeah, okay. So we don't have any hydronium ions, we've only got the hydroxide ions. So our POH is equal to the negative log of the OH minus concentration. I know this sounds dumb putting always this out, but please show full working. Don't just sort of go, oh, I've got this, plug it into the calculator and get the answer. You're much more likely to make a careless error if you do that. So rather write out that you're doing the POH, getting the POH answer, then calculating the pH. Because I've sometimes seen students writing the POH, but because they haven't shown the full working, they've got confused in their mind and they thought they were calculating the pH instead of the POH. So we just do that negative log of 0.267, and if I just get my calculator, so that would be 0.267 log, and you get an answer of negative 573, negative 0.573, and come on. And what I've forgotten, of course, is to put that first negative in. So, as I say, this step you don't really have to put in 573. Okay, so that's your POH, and now we want to calculate the pH. And so your answer is going to be then 14, subtract that number. And normally when you've got that as a negative, I tend to just say plus 14 and get the answer. So your answer is going to be 13.426, and then we'll sort it out. So it's 13.426. But remember, keep it to 1. So the first negative is, remember we said it was an inverse scale. So that's just from that negative that's coming down all along. This bit over here is the answer to the log of that. So you always come up with a negative number, very likely, and then you multiply it by negative and you get a positive. Okay. Right, now you're not going to get full marks, even though strictly speaking that actually is correct. It's 2 3 significant figures because of the. I found in the past examiners do not like that. So rather round it off to either 3.4 or, sorry, 13.4 or 13.43. Okay. So any questions about calculating pH? No? Okay. In the last few minutes, we're going to do the inverse. Okay, so in other words, I give you the pH, and you must calculate the concentration of the hydronium ions. I don't think they'd ever ask you to calculate the concentration of hydroxide ions, but who knows, they could. So let's go, so we've got something over here. Say I have a pH equal to 4.5. What is my hydronium ion concentration? So pH is equal to the, come on, negative log of the hydronium ion concentration. So I've got to try and get this by itself. So I've got to get rid of the log. How do I get rid of a log? you take the inverse log or the anti-log or something like that, which is pretty much 10 to the. Okay, so if I have, for example, a pH of 4.5 is equal to negative log of H3O plus, then if I take the inverse log, it'll be 10 raised to the power of 4.5 is equal to, now, actually, one step I should have got rid of first. Your first step is actually to get rid of this negative value. So to get rid of the negative, because there's two things I've got to get rid of. I've got to get rid of that, and I've got to get rid of that. So the first step is to get rid of the negative. So I multiplied both sides by -1, and I'll come up with this step. Okay, you with me so far? I've got rid of this negative in front of the log. The next step is to do the inverse log, which is basically raising it, you know, so it'll be 10 to the negative 4.5, because 10 to the log is equal to, you know, it cancels out, so that is equal to the hydronium ion concentration. Okay, so to work out the pH, you would then just so it's 4.5. Okay, let me make sure it's clear. 4.5 negative and 10 to the x. You raise it up. Can you see I've got 3.16 times 10 to the minus 5. I hope you can see that e to the minus 5. So now I have got, oh, what was it? 3.16 times 10 to the minus 5. I'm not quite sure why it's not writing properly. Okay, so that's my hydronium ion concentration. I won't get excellence for this. Why not? What have I forgotten? The units. Okay, so I've got the right number of significant figures, but I haven't got the units. So you make sure that you put the, oh, come on, moles per liter is equal to the hydronium ion concentration. Okay, and you do that for, you know, given any pH. You could work out the hydronium ion by doing the inverse log. So first transfer across the negative and then do the 10 to the. Okay, time's up. And as I say, I would love to have some feedback